All right, so good afternoon. Let us continue our lecture today. So last time we was trying to solve the heat equation, right? You have a function u, which depends on time and space, all right? And you want to solve this partial differential equation for x to be in 0L, and t is from 0 to infinity. All right, and we have boundary condition. We have that ut at 0 will be ut at L level 0, and the initial condition is u 0x is going to be x. Right, so this is the heat equation that we were trying to solve in the previous class. So this equation is the partial differential equation because it depends on t and x. So in this equation, you have the partial derivatives in t and in x, which means that this is the partial differential equation. You have the boundary condition at 0 and L, because you have a second derivative in x of u, so those are boundary conditions. And you also have the initial condition at 0, right? So u0x is equal to x. So you need, yes?
As you probably see with this event here, if you need to go to the restroom, leave early, go to these stairs, go up through the English suite and out the back. That's really it.
All right.
When's it over? Okay.
All right. So so now the idea is again to construct a basis, right? Construct a basis. For x, right? So we know that we don't have to construct a basis for both x and t. We just have to construct a basis for x. So the basis for x can be computed by solving the Stub-Levin Eigenvalue problem. All right. So you have the phi prime second is equal to lambda at phi. X is going from 0 to L, and we employ the same boundary condition, right? It's equal to 0, right? So in order to have a basis, we know that we have to do the eigenvalue problem, right? So we solve phi second is equal to lambda phi for x in 0L, and phi 0 is equal to phi L, and this is 0, right? So we only solve it in the x variable. We don't have to do it in the t variable. So in the previous class, we computed, and phi n of x will be sinus of n pi x over L. And the lambda n is going to be minus L pi over L squared, right? So this is what we found. So which means that if you take the second derivative of phi n, you're gonna have minus n pi over L squared times sinus of n pi x over L, and this is minus n pi over n squared phi n of x. All right. So we solved and we found that we have the eigenfunctions sinus of n pi x over L, and we found the eigenvalues to be n pi over L squared, which means that if you take the second derivative of sinus, you get minus n pi over L squared times sinus, right? All right. So now we're gonna do the expansion, right? Since phi n x forms a basis, we can expand. So you have utx is going to be the sum when n is going from 1 to infinity of an t times phi n x. Right? Because this is a basis, you can expand or you can do a projection of phi of u onto these spaces, right? Right. So what is the value at the point x is equal to 0 of u?
0.
Why?
Satisfied by the eigenvalue problem.
Yes, can you sign the back of the paper, please? All right, so if you consider ut 0, so you're going to have this sum of a and t, and 0, and this is 0 because of this boundary condition. All right? And it's going to be the same for L, right? A and t, P and L, and this is also 0. So both of them are 0. Right? Questions? Which means that this boundary condition is satisfied. It's good? Questions? Right. So now we're going to try to solve this equation. All right? So in order to solve this equation, we need to compute the derivative of t and the derivative of x, and they're equal, right? So what is the partial derivative in t of this function u? Yes?
The sum of when n goes from 1 to infinity, an prime t bn.
Can you sign the by the paper, please? So, in order to compute the derivative in t of this series, what you have to do is you compute the derivative with respect to an, right? An t prime times phi and x. All right? What is dxx of u? Right, so I have this series, an phi n, and I want to compute a second derivative. Yes? Yes, can you sign back the paper, please? So I have ux is this sum, right? And I want to take the derivative in x, which means that I have to take only the derivative of this guy. An t of phi n second of x. All right? So what is phi n second of x? Yes? Yes, can you sign the back of the paper, please? So now because of this property, right? Because of this, you can replace this by lambda n of phi n. So we have a n t lambda n of phi n t. All right? It's good. Right? So because of this, I plug it back here. And I have lambda n second is going to be lambda n phi n. Right? So now I go back to this equation. I have dt of u, tx is equal to dxx of utx. What happened? What can I say about the coefficient an? Yes?
Is it Bn of x or Bn of t?
Thank you. Can you sign back up this? This is x. Right? So now let us come back to this equation. You have ut, dt of u is equal to dxx of u. Right? Which means that this guy is equal to this guy. What can you say about the coefficient? Yes?
An of t is equal to an prime times lambda.
Yes, can you sign back the paper, please? So because this guy is equal to this guy, the coefficient here has to be equal to the coefficient here, right? So, which means that an prime t has to be equal to lambda n of t. So basically this is the first order differential equation. How can we solve it?
Didn't we say it was a separable?
Yes. Can you sign back the paper, please? So from the previous class, we know that this is a first order differential equation and it's separable. So we also solve this equation. So the solution for this equation is e to the minus lambda n an of 0. Right? Questions? Right, so now this is first order differential equation, and this is separable. So you can solve it, and an is going to be exponential minus lambda n at 0. Right? So now I'm gonna plug this formula into the formula over there. So I'm gonna plug it here. So let me erase here. So this is going to be the sum when n is going from 1 to infinity of a n of 0 times exponential minus lambda n t 3n of x. Alright? So I replace this to this. And this is the solution of heat equation. But I still miss something. Right? So I explain again. After you identify the coefficient, you find that an prime of t is lambda n an. Alright? This is the first order differential equation. And you can solve it by the method, the separable method that I discussed in the previous class. And ant will be exponential of minus lambda n at 0. So I plug this formula back to this formula. And ut will be the sum when n is going from 1 to infinity of an 0 exponential minus lambda n t 3n of x. Right? Basically, this is the solution of the heat equation, but there's something missing. What is it? This is close to the final solution, but there's still something missing.
The weight?
No. So here you know what is lambda n, right? So you can replace it, right? So you have n is going from 1 to infinity of an 0. So lambda n is this guy. So I have n pi over L squared t, and then I know what is 3n. So this is sinus of n pi x over L. But I said this is not yet a solution because, yes?
The initial condition?
Yes. Can you sign the back of a paper, please? So in this formula, everything is explicit except an 0, right? We don't know what is an 0. Right, so I said that this is a solution given the fact that I know what is an 0, but I don't know what is an 0, right? How can I find an 0? There's one thing in the equation that I haven't used. Yes?
You have 0 x, is it?
Yes. So I have to compute an 0 using this condition, right? So now everything is explicit. This factor is explicit, this factor is explicit, except an 0, right? So I have to compute an 0. To compute an 0, I'm going to replace t to be 0. So this is x, right? By this initial condition, right? So we know that at t is equal to 0, u of 0x is equal to x, right? So what is the series with respect to t is equal to 0? Yes?
E to the negative lambda t sine n pi x over L.
No, I went at t is 0. At t is equal, at
T is equal to, yeah.
it's going to be?
Oh, it's gonna be sine n pi x to the over L. Am I getting it wrong? I'm getting it wrong.
Yes?
So would it just be an of 0 times sine n pi x over L, therefore our an of 0 is equal to negative sine n pi x over L?
I just want to say what is the series. I want to know what is the series of u when t is equal to 0. What is this series? I have this series. What is the series in this case of t is equal to 0?
X.
Well, even 0 would just be 1, right?
So what is the series in this case? Yes?
Someone n starts at 1 to infinity of sine n pi x over 1.
Yes, can you say it back and forth, right? So I just replace t to be 0. So the series will be the sum when n is going from 1 to infinity of an exponential of 0 sinus of n pi x over L. Right? I just have to replace t to be 0. So which means that x is the sum when n is going from 0 to infinity of an at the point 0 sinus of n pi x over L. Now I want to compute an. How can I? Right? So I explain again. I have this series that I computed from the equation, right? an0 is unknown. I have to compute an0. But I know in advance that at 0, at t is equal to 0, this function is x, which means that if I replace t to be 0, I'm going to have this sum. But when t is equal to 0, e to the 0 is 1, so I have x is equal to this sum. And I want to compute the coefficient an 0. Yes?
You expand x's into the eigenfunction.
How do you expand it?
X is equal to the sum of n from n equals to 1 to infinity.
So in this expansion, what is the formula for an? No. In this expansion, I want to know the formula for an.
Would it not be your original idea of the inner product?
Right. Right. So to compute an0, you just have to use the fact that all of these are orthogonal, right? So you're gonna have to integrate from 0 to L. You're gonna have to inner product with sinus, right? So you have x sinus of n pi x over L. And then this is going to be a 1, 0 sinus of n pi x over L. Sinus of n pi x over L. You take the inner product. And then you have an is 0. Sinus of n pi x over L. Sinus of n pi x over L. Plus everything, right? So this means that you have to take the integral from 0 to L of x sinus of n pi x over L dx, which is a1 is 0, integral from 0 to L of sinus of pi x over L times sinus of n pi x over L dx plus an is 0, integral from 0 to L sinus of n pi x over L square dx. Right? To compute an, I just have to inner product that with the sinus. But you know that those functions are orthogonal in the sense that this is 0, everything else is 0, except this guy. Right? Questions? Explain again. So you have x is the sum of an sinus n pi x over L. Right? To compute an, I just have to inner product that with the function sinus n pi x over L. Right? So I'm going to inner product x with sinus. Sinus pi x over L with sinus n pi x over L, and 0 with sinus n pi x over L with sinus n pi x over L. Right? So which means that these I have to integrate, this I have to integrate, and this I have to integrate. The inner product is the integration. Yes?
Never mind. Well, I mean, so, but don't we know sine is an odd function?
So everything is 0, right? So
Yeah.
because they are orthogonal, everything is 0.
Okay.
Right? So when you inner product, the only thing left is this guy.
Yeah.
So which means that an integral from 0 to L of sinus of n pi x over L dx is going to be an at 0, integral from 0 to L of sinus of n pi x over L square dx. Right? Questions? Right? So when you inner product this series with sinus, everything else will be dropped except the sinus n pi x over L and sinus n pi x over L, which means that the inner product of x with sinus n pi x of L will be an0 times the inner product of n sin x of L with itself. Right? It's clear? Right, so now I can compute an0. an0 will be the integral from 0 to L of sinus of n pi x of L dx divided by the integral from 0 to L of sinus of n pi x over L.
Whatever the x in the numerator.
Which x? Thank you. Can you sign back the paper, please? Right? So when you inner product sinus n pi x over L to everything, this is equal to, so this is a drop because this is 0 because they are orthogonal. The only thing which is left is this guy, right? Which means that an will be this guy divided by this guy. Questions?
In the A1 term, isn't that the case where n is equal to 1? So why is there still the n in the second sign?
So this is n equal to 1 and this is n is different from 1. So this is 0.
Okay.
So if n is different from 1, but if it is not different from 1, then this is not 0, but the other guys will be 0. Alright? It's good? Right? So basically an is 0 will be n x sinus n pi x over L times integral from 0 to L sinus n pi x over L squared. Alright? Now I have to compute a and 0. I have to do this integration and then I plug it back to the solution series, and then everything will be done. Alright, so let us compute integral from 0 to L of x sinus of n pi x over L dx. Yes?
Could you calculate the denominator first? Just because isn't that going to be something?
This, which one? This one.
Oh, no, never
No,
mind.
this is
I'm
not
not,
so.
I'm
Because
never mind,
the-
never mind.
yeah.
Sorry.
This is going to be half and half, yes. Who said that? You said that? Okay, can you set aside by the paper, please? So now, so I have to take the integral from 0 to L x sinus n pi x over L dx. So this give. So how do I do this computation? Yes.
The U, B.
Yes. So you have to do integration by part,
Yeah.
right? So you have udv is uv minus vdu, right? So in this case, I have integral from 0 to L of x cosinus of n pi x over L minus divided by n pi x over L. So this is this, right? So I observe that sinus is the derivative of minus cosinus, but I have to divide by this factor, right? And so this is going to give me the integral from 0 to L of x d of minus cosinus of n pi x over L n pi over L. Right? Now this is u and this is dv. Questions? Right, so now I have to compute this guy using integration by part. The integration by part formula is always u dv is uv minus vdu, right? So I know that sinus is minus cosinus prime will be sinus, but of course I have to divide by the factor. So this gives me x df minus cosinus n pi x over L n pi over L. So this gives me x minus cosinus of n pi x over L over n pi over L. And I have to evaluate 0 and L. So the leftover will be this guy. So this is uv. Now I have to minus vdu. So vdu will be minus cosinus of n pi x over L over n pi over L. And I have to integrate this from 0 to L. So this is v and this is du. Right? It's clear. I explain again. Now, in order to compute this a and 0, I have to do integration by part. I have the interval from 0 to L of sinus, x sinus. So the sinus is the derivative minus cosinus. So I have du dv. I use this formula. I have uv, evaluate that at 0 and L, minus vdu. Right? Right, so let us compute this. Right, so I'm gonna leave only this formula. And so this is the solution I'm gonna use later. Alright, so for this guy, I have to plug L into the formula. I have L minus cosinus of n pi over n pi. The other term is 0 because I replace 0 into x. Alright, so plus 1 over n pi over L, integral from 0 to L of cosinus of n pi x over L dx. So what is the value of this guy? Yes?
0.
Why?
Because it's gonna integrate to sine of n pi x over L, and sine of n pi is 0.
Yes, can you sign the paper, please? So here I have L over n pi minus of minus 1, so which means that this is n plus 1, right? The other term, I have 1 over n pi over L, sinus of n pi x over L over n pi over L, and a value at 0 and L, so this is 0, right? So basically the first guy gives me minus 1 n plus 1 L over n pi. I explain again. So here, after I do the integration by part, this term, I have to evaluate that as an L. This is L, so there's an L here, so this is L squared. So this guy, I have to evaluate that at L. So when I replace L here, I have L minus cosinus n pi over L. And I have to evaluate that at 0, but at 0, this x is 0, so I don't have to worry about that anymore. So for the second term I have 1 over n pi over L, and I integrate from 0 to L of cosinus. So the antiderivative of cosinus is sinus. I evaluate at 0 and L, so this guy is 0, right? So this guy I have L squared over n pi minus cosinus n pi is minus 1 to power n, but I have to add one more minus, so it's minus 1 to power n plus 1. Questions? Right, so let us compute the second term, right? So I have to compute the second term, the integral from 0 to L of sinus of n pi x over L squared dx. Now what is the formula that I need to use? Yes?
1 minus cosine pi x over L divided by 2.
Can you sign back this? So I have sinus of n pi x over L square will be 1 minus cosinus of 2n pi x over L and over 2, right? So which means that this guy will be integral from 0 to L of 1/2 minus cosinus of 2n pi x over L and 1/2, and I have dx. So what is the next step? Yes? Yes. Can you sign the back paper, please? So for this one, you're gonna break it into 2. So you have integral from 0 to L of 1/2 dx minus 1/2 integral from 0 to L of cosinus of 2n pi x over L dx. So what is the value of the first guy? Yes?
1/2.
1/2. Can you sign back to paper, please? So it's 1/2, but remember that you have the L, right? So for the second guy, how can I compute that? Yes?
It's gonna be sine 2n pi x over L over 2n pi times 1/2, but the x is an L, so it'll end up being 0.
Right, and sine the back effect of this. So here I have 1/2 of sinus of 2n pi x over L over 2n pi over L, but I have to evaluate 0 and L, and remember this is 0. So basically here I have to divide by L over 2. Alright? Questions? So this A and 0, so when you divide by L over 2, you're going to have 2 L over n pi minus 1 and plus 1. Right? So I divide L squared by L over 2, this gives me 2L. Right? And here I have n pi, here I have n pi, here I have minus 1 and plus 1. So the formula that I have here will be the sum when n is going from 1 to infinity of 2L over n pi minus 1 n plus 1 times exponential of n pi over L squared t sinus of n pi x over L. Right? And this is the solution. So after you compute a and 0, you just have to plug it back here. So this is a and 0, and this is, you keep the other term, so you keep exponential of n pi square over n L t, and you keep the sinus, right? Questions? It's clear? All right. So all right, so now let us try to understand what is going on so where's the equation coming from, right? So now let us consider the origin of the equation, the D equation. Right, so let UTX be the concentration. So this is basically a diffusion equation. Concentration of dye and position x in a pi at time t, right? So now you consider a pi, and the pi is going from 0 to L, and this is the x, position x. And in the pi, you have a line with concentration UTX, right? Right. So I explain again. Now I have a pi going from 0 to infinity or whatever, and in the pi I have a dye, and I call the concentration of this dye and the position x and time t to be UTX, right? So now if I consider the total mass from position x1 to the position x2, right? The total mass of the dye from x1 to x2 will be right. Suppose that I have UTX is the concentration of this die. So what is the total mass of the die from this position of the pi to this position of the pi at time t? At time t. Right, so the concentration is used Tx, and I want to compute the total mass of the die from position x1 to position x2. This is UTx. This is a concept, yes?
Would be the integration of UTX
Yes.
from x1, x2.
Yes, can you send by the paper, please? So I'm going to have to integrate from x1 to x2 of UTx dx, right? Because the concentration is UTx. So if you want to compute a total die in that interval from x1 to x2, you have to integrate from x1 to x2 of UTx, right? Right. So the change in time of m, the variance in time of the total mass is computed by dmt over dt, and this is d over dt of this quantity utx dx. Right? So if I want to see the variance in time of the total mass of the die from position x1 to x2, I'm gonna have to differentiate in time this quantity, right? So what is this derivative? Yes?
It just ends up being UTX.
Yes. So can you send back the paper, please? If you want to take the derivative of this guy, you have to take the derivative of the guy inside, right? Because the integration is in x. It doesn't affect the t variable, right? So this gives you integral from x1 to x2 of dt of u tx dx. Right? It's clear? So then you're gonna have the derivative in terms of the total mass will be the integral from x1 from the integration from x1 to x2 of dt of utx dx, right? So now suppose that I forget about what happened outside. So there's something called Fick law. Fick laws. The Fick law says that the change of the mass of this material, the die inside this pipe, will be measured by the difference, the change of on the variance of the total mass inside a pipe will be measured by the difference so you have dx of u x as t2 minus dx at u t x1, and this is time k. So k is a constant. Is a constant depending on the type of die inside the pipe. Right? So there's a law which says that, okay, if you want to measure the change of the total mass of or the variance of the total mass of the die inside this pipe from x1 to x2, what you do is that you measure the difference between the density and the points x2 and the point x1, and the change of the density will be dx of u, right? So you measure the change of the density, which is the derivative of the concentration, and then you subtract the two quantities x2 and x1, and you multiply that with a constant, and this constant depends on the type of the die that you want. So now I have an equation. Can you tell me what is the equation? I explain again, right? So now I consider a die or a material inside this pipe, right? So you inject the die into the pipe, and you inject it at point x1 and and it's going out at point x2, right? So the concentration of this guy, the die, is UTX. So the mass inside this pipe will be the integral from x1 to x2 of UTX dx, right? And if you want to see the change of the mass going back and going inside this pipe, you have to take the derivative in terms of this quantity empty, the total mass, right? But there's a law of physics which say that, okay, if you want to see the change of the total mass of the die inside this pipe, what you do is you consider the change of the density. So the change of the density is measured by the derivative in x of the density, right? So you measure this change at the point x2 and the point x1, and you take the difference. And you multiply that with a constant, which depends on the type of material, the die that you have. And this is the change of the total mass inside the pipe. Now I have an equation. What is this equation? Yes?
It's the second partial derivative of x of u tx.
No. I said that now this is a little bit further, right? So now directly from here I have an equation. Yes?
Well, using the way you have it fixed law, don't you just end up getting the heat equation when you plug it in with respect to, because you have the constant, right? And then if you have dx utx2 minus dxu tx1, isn't that related to the mass in that case? So wouldn't you just end up getting the heat equation?
Yes. Right. So yes, but this is really fast. Can you send back the paper, please? So I can see that, okay. So the variance in time of total mass is this guy. But the variance in time of the total mass is also this guy, right? So this is the first guy, and this is the second guy, right? Which means that they have to be equal. So now they have to be equal, right? So you have that the integral from x1 to x2 of dt of u tx dx is then equal to dx of u tx2 minus dx of u tx1. And then I have to multiply that with a constant k, which depends on the type of thing that you have. So this guy has to be equal to this guy. Now I have the heat equation y. Yes?
If you take the derivative with respect to x on both sides, you end up with partial differential t of utx equals second partial difference.
Yes, can you send back the paper, please? So now I take the derivative with respect to x2, right? So then I have dt of u tx is equal to k dxx of u tx, right? Now, in this equation, I just take the partial derivative with respect to x2, this gives me x2, and then here I take the partial derivative with respect to x2, and then I have this guy. So basically, this is the diffusion equation. So the diffusion equation describes the fact that you put dye into a pipe and it's diffused, right? But this is not only for dye, it's also for heat, right? So if you put heat here, the same thing happens, and then you get the same equation, right? So this is equal to heat equation, because if I replace dye by heat, the same idea applies, right? Any questions? So the key idea is very simple. You compute the total mass from x1 to x2, which is the interval from x1 to x2 of utx dx. So the change of the total mass will be the derivative in terms of this quantity, right? But the change of the total mass can also be computed by taking the change in x2 minus the change in x1, right? And these two quantities are equal, right? So here I have an integration in x, here I have a derivative in x, here I have a derivative in t. So now I take the derivative in x here, so I have the derivative in t will be the second derivative in x. And this is the diffusion equation or the heat equation that we are solving. Questions? It's clear? Right, so now if there's no questions, let us go back and try to solve another heat equation. What?
Music.
Yes. Right. So let us solve another heat equation. Any questions on the meaning of the physical meaning of the heat equation? It's good. Right, so let us solve the following heat equation. So the heat equation right, you have ut, dt of u, tx is equal to the xx of utx, right? So you solve it from minus L to L, and t is from 0 to infinity, right? So I have this boundary condition. I have u of t, and minus L is equal to u of t, at L, and derivative in x of ut minus L is also equal to derivative in x of ut at L, and u 0x is equal to 1. Right, so this is the heat equation that we will try to solve. Right? So in this case, I have the same heat equation. I have derivative in time of u is the second derivative in x of u. The equation is solved on minus L to L with time is going from 0 to infinity, right? So I have u at minus L is u at L, the x of u at minus L is the x of u at L. U at 0, which is the initial condition, will be 1. So what is the eigenvalue problem that I have to solve now? We know that we don't have to solve for t, right? So we have only to solve for x, and in order to do that, we need a basis. In order to have the basis, we have to solve the eigenvalue problem. What is the eigenvalue problem in this case? It's going to be what? It's going to be phi second is equal to lambda phi, right? You solve it from minus L to L. And I need the boundary condition. What is the boundary condition?
phi of negative L equals phi of L.
Yes.
And phi prime of negative L equals phi prime of L.
Right. Can you sign back the paper, please? So,
How do you know that?
I have, no what?
How do you know those two boundary conditions?
Yes. So the boundary condition has to be, so it has to be the same with this one, right? So you have what? You have ut minus L is equal to utl. I just forget about the t, because here I have only x, right? So this is, right? First I forget about the t, now I replace u by phi, right? For the second one, you have dx of ut minus L is equal to dx of utl, right? So I forget about the t, and I replace that by phi, right? Yes. So basically, this is how you construct the boundary condition, and I'm gonna show you in a minute. But if you solve this guy, when you expand a series, you plug it back and you get exactly that boundary. Yes.
Why can you get rid of t?
Right. So the idea is what? The idea is you expand this in terms of x, and the coefficient depends, right? So this is the basis. You expand u on this basis, but the coefficient will be depending on t. T you don't care because you're gonna solve it like a first order differential equation, right? So now you only care about x, right? Right. So yes. So this is the eigenvalue problem. Eigenvalue problem. So how can I solve this equation? What should I do to solve for this eigenvalue problem? This was the midterm one, right? So how can I solve it?
Do like heuristic equation?
Yes, can you send back the paper, please? So now what you do is you go to the characteristic equation. R squared is equal to lambda. And if you remember from midterm one, what kind of basis should we get from this eigenvalue problem? Yes?
You end up just getting case 3, which
Yes.
and the cosine would cancel out, so you would just end up getting the sine. And the cosine.
Yes.
You get the Fourier basis?
Yes. Can you sign back the paper, please? So basically, this is a periodic boundary condition, right? Phi of minus L is equal to phi of L. Phi prime minus L is equal to phi prime at L, which means that this is a periodic function, right? So for periodic function, we know that this is Fourier basis, right? Right. So now let us show that this is the Fourier. So I consider this characteristic equation, case number 1. Lambda is positive. So what happens when lambda is positive? Yes?
No, r equals plus or minus the square root.
Yes. Okay, stand back the paper, please. Now when lambda is positive, I have two roots, right? Plus or minus square root lambda. So when I have two roots, what happens? Yes?
Your solution B equals C1 e to the plus C2 e minus square root.
Yes, can you say it back the paper, please? So you have x is c1 e to the square root of lambda x plus c2 e to the power minus square root of lambda x. So what is the next step? Yes?
Plug in your condition that phi of negative L equals 0.
Yes, can you say it back the paper, please? So now I'm gonna use the first boundary condition, right? So I have phi L is equal to phi of minus L, which means that c1 e to the square root of minus lambda L plus c2 e to the square root of lambda L, and this is equal to c1 e to the square root of lambda L plus c2 e to the power minus square root of lambda L. so I have to plug minus L and L, so phi minus L is phi L. So which means that here I have C1 is square root minus lambda L plus C2 is square root lambda L is C1 is square root lambda L plus C2 is square root of lambda L. Right? What is the next step? Yes? Yes. Okay, send back the paper please. Now I group C1 and C2, right? So I have C2 e to the square root of lambda L minus e to the minus square root of lambda L is C1 is square root of lambda L minus, right? So now I group C1 and C2. I group this C2 with this C2 and this C1 with this C1. So what I get is C1, C2 is square root of lambda L minus e to square root minus e to the minus square root lambda L, and this is C1. What is the next step? Yes?
You can divide the e to the square root of the inner equation
Yes.
on both sides, so C2 equals C1.
Right. Can you say the back of the paper, please? So then you have C2 minus C1 e to the square root of lambda L minus e to the is equal to 0. But to get C1 is equal to C2, I have to pay attention to one thing. I have to show that this guy is positive. How can I show that this guy is positive? Yes?
It's 1 over e to the square root of lambda, so smaller than the first one.
Okay, so I'm back to this. So we know that this guy is bigger than 1, and this is bigger than the inverse of this guy. And this is, right? So we know this, right? This guy is bigger than 1, so which means that the inverse of this guy has to be smaller than 1, which is e to the power minus square root of lambda L, right? So which means that C2 has to be equal to C1, right? So now I have phi x is C1 e to the square root of lambda L x plus C1 is minus square root of lambda x. Phi prime of x will be C1 square root of lambda is square root of lambda x minus C1 square root of lambda is minus square root of lambda x. Alright? I have to take the derivative because I want to use the second boundary condition. Right. Now I have what? Now I have phi prime minus L is equal to phi prime at L. And this gives me C1 square root of lambda is square root of lambda L minus C1 square root of lambda is square root minus lambda L is equal to C1 square root of lambda minus square minus square root of lambda L minus C1 square root of lambda is square root of lambda L. Right? So so after I found that C1 is equal to C2, I plug it back to the equation to the phi. So I have phi x is C1 e to square root of lambda x plus C1 into square root minus square root of lambda x. Now I have to take the derivative because I gotta use the second boundary condition, right? So when I use the second boundary condition, I end up with this equation. What happened? Yes?
C1 equals 0.
Yes, can you send back to paper, please? So in this case, C1 is 0, right? So because C1 is 0, there's no eigenvalue, right? Right. So case number 2. So case number 1 is always the easiest case because you know that there's nothing happened there. Now case number 2. Right? Case number 2, lambda is 0. When lambda is 0, this is an interesting case. What happened when lambda is 0? Yes?
We know phi of x equals ax plus b.
Yes, can you say it back to paper, please? So when lambda is 0, this gives me 0, so phi x is ax plus b. What is the next step? Yes?
Plugging your initial condition.
Yes, boundary. Can you say it back to paper, please? So now you plug the first boundary condition. right? So in this case, you have ax, a minus l plus b, is al plus b, which give me 2al is 0, which means that a is 0. So phi x is then p, right? Okay. Right, so I explain again. When lambda is 0, phi second is 0, which means that phi x is ax plus b. You have phi minus l is phi l, which means that a minus l plus b is al plus b. This gives me a to l is 0, so a is 0, which means that phi x is b. Right? So when phi x is b, fifth power of x is 0, which means that the second boundary condition is always satisfied. Right? So what is the conclusion in this case? Yes?
We can set b in the, because since b is an solution, we can set it to be some constant, so
Right.
1.
Right. So in this case, b is a constant, right? So you can remove it. And so in this case, you have an eigenfunction, which is 1. And what is the eigenvalue?
0.
Yes, can you sign back paper, please? The eigenvalue is 0. Right? So the second case in this case is interesting because it gives you one eigenvalue and one eigenfunction. Right? So it is not trivial like the previous case. Case number 3. So case number 3, so you have lambda is negative. So when lambda is negative, you have what? Phi x is. Right. So first, what are the values of the two roots? Yes.
It'd be plus or minus I times the square root plus
Yes.
absolute value of lambda.
Can you sign the back of paper, please? So in this case, the two roots will be plus or minus I times the square root of the absolute value of lambda. What is the form of phi? Yes.
Cosine square root lambda. Then
Sine.
sine, yeah.
Can you sign the back of paper, please? C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x. Right? This is the form of phi. Okay? Now, what is the next step?
Plug in a boundary.
Yes, can you say the microphone, please? So now you're going to plug in the boundary condition. Phi L is phi of minus L. So I have C1 cosinus of square root of lambda times L plus C2 sinus of square root of lambda times L. And this gives me C1 cosinus of minus square root of lambda L plus C2 sinus of minus square root of lambda times L. Right? Right? So I plug the second boundary condition I had. At the first boundary condition I have phi L is phi of minus L, which means that C1 cosinus square root of lambda is plus C2 sinus square root of lambda is equal to C1 cosinus minus square root of lambda plus C2 sinus minus square root of lambda L. Right, so what is the conclusion that we have for this? Yes?
Well, we know since cosine is an even function, the negative in this case, so cosine negative square root of lambda L is equal to the same thing as cosine square root to absolute value of lambda L. And
Yes.
since sine is an odd function, we know that sine negative square root of lambda L is minus c sine.
Right. Can you sign the back of paper, please? So, because you know cosinus of minus and cosinus of plus, they're equal, and cosinus minus, sinus of minus is minus sinus. Right, so I can replace this by this one. So basically this and this guy cancel. So I have sinus of square root of lambda L is 0. So what is the value for lambda? Yes?
Oh, you just set the square root of lambda L equal to n pi.
Can you send it back to paper, please? So this gives me square root of lambda L is equal to n pi. All right. So lambda will be minus n pi over L squared. Right. So now I have to plug this to the form of phi, where px is c1 cosinus of n pi over Lx plus c2 sinus of n pi over Lx. Right? Now I take the derivative, so this derivative will give me c1 minus n pi over L sinus of n pi x over L plus c2 cosinus of n pi over L cosinus of n pi x over L. Right? So now I take the derivative of this guy so that I can check the second boundary condition. So I have phi prime of x is minus c1 n pi over L sinus plus c2 n pi over L cosinus. All right? And of course, this is equal. This is satisfying because it's periodic. Right? So what are the eigenfunctions for this problem? Yes?
Like you said already, the Fourier basis, so 1, then cosine impact over L sine impact.
Right. Inside the back. So after finish all of those computation, we find the basis. Right. 1 cosinus of n pi x over L sine n pi x over L. Right? So for this one, eigenvalue is 0. For this one and this one, eigenvalue is minus n pi over L squared. Right? Right. So I explain again. So after I do all of those computations, I end up with this basis 1. I have cosinus and sinus. Right? So for the 1, the eigenvalue is 0. For the cosinus and sinus, the eigenvalue is n pi over L squared. Basically, this is Fourier basis. Right? This is Fourier. All right. All right. So now I'm gonna have to write UTX on this basis. So this is gonna be A0 of t plus times 1 plus the sum when n is going from 1 to infinity of an t cosinus n pi x over L plus bnt sinus of n pi x over L. Right? Right? So now I have the basis 1 cosinus n pi x over L sinus n pi x over L. I have to write the solution on this basis. So the only difference between the heat equation and the previous equation is that all of those coefficients depends on t. Right? So you see that in all of those coefficients you have t dependence. Right? So in the previous problems, we don't have t dependence because the solution is not doesn't depend on x. But in this case, the solution depends on t. So I have to write on this basis the solution in terms of still on this basis, right? So you have the basis for x, but the t coefficients they have to be in an and bn. Right? Questions? Right. So now I want to check the first boundary condition. I said that the first boundary condition is satisfied. Why? Yes?
Still periodic.
Right, because of the basis, the eigenfunction that we can send by properties. Because the eigenfunction that we found satisfy this condition, right? Which means that UTL has to be equal to UT of minus L. And cosinus of n pi L over L plus BNT sinus of n pi L over L is equal to, this is equal to U ANT plus this sum AN cosinus of n pi minus L over L BNT sinus of n pi minus L over L UT of minus L. Right? So, because all of those functions that we found satisfy the boundary condition phi of minus L is equal to phi L. So when I expand, this cosinus n pi L over L is equal to this n pi minus L over L, and n pi L over L is equal to sinus of n pi minus L over L, which means that UTL has to be equal to UT minus L, right? So this is why the reason that we choose this boundary condition to be the same with this boundary condition here, because at the end when you expand, they coincide, right? It's clear? Right, so again the second boundary condition will be the same. I'm gonna show you. So if I have this series, what is the derivative in x of this series? I'm checking the second boundary condition, which is this one. In order to check this, I want to compute the derivative in x of this series. What is it? Yes?
The series from n equals 1 to infinity of n pi over L A N T cosine of n pi 0.
Can you send it back up, please? Right, so if I want, now I want to check the second boundary condition, what I do is I take the derivative in x of this guy. So this gives me the sum when n is going from 1 to infinity of ANT. So this gives me the derivative of this guy over L prime plus BNT of sinus of n pi x over L prime. Right? So if I want to take the derivative in x of this series, I just have to take the derivative in x of all of the terms that we have there. All right? Right. So now I want to show that the two things here are equal. I replace it by L. Right? And so you have dx of ut minus L and 1 to infinity of ANT cosinus of, this is L, n pi minus L over L prime plus BNT sinus, cosinus, sinus n pi minus L over L prime. Right? Right? So I want to check that the x of u at minus L is equal to the x of u at L. So I just have to replace in the derivative L at minus L. And they're equal because this guy is equal to this guy, and this guy is equal to this guy because they appear a bit. Right? Questions? Right, so basically, because you choose the same boundary conditions for the eigenfunctions, these two boundary conditions are satisfied. Questions? It's good? Right. Right. So now what I have to do is I have to solve the equation. So what is the derivative in terms of utx?
be equal to the second derivative.
No, no, I'm just
Oh.
trying to say the
Oh.
derivative of this series.
It'd be the sum from 1 to infinity of an of t lambda n cosine n pi x over L plus b n of t lambda n sine n pi x over L.
I just want to take the derivative, this guy. What is it?
A naught prime of t plus summation of n prime
Yes,
t
so-
cosine plus b n prime t.
So I just have to take the derivative with respect to t in this series, right? So this is an prime cosine s of n pi x over L plus bn t prime sin s of n pi x over L. All right. So in order to take the derivative in terms of the function u, I just have to take the derivative in terms of all of the coefficients. Now I want to take this derivative in x of u tx. What can I do? Yes?
Just make all of those double prime.
Yes, can you sign the blank paper, please? So I just have to take the derivative of everything in t. So the first one will be will disappear. So we have cosine s n pi x over L plus bnt sin s of n pi x over L double prime. Right? Right? So first I take the derivative in t of u by taking all of the derivative in all of coefficient, and I take the second derivative in x of u by taking all of the second derivative in x of all of the function. What can I say about cosine s and sin s second? Yes?
Well, so aren't they originally part of the basis of phi n or eigen function, right? And so couldn't you say they were lambda and
Right. Can you sign the back paper, please? So this guy I can replace it by using the eigenfunction property. So I have ant lambda n cosine s of n pi x over L plus bnt lambda n sin s of n pi x over L. Right? Because we know that phi n second is lambda n phi n, right? Which means that the second derivative of cosinus is lambda n cosinus. The second derivative of sinus is lambda n sinus. Now, we know that this is equal to this because of the equation. So what can I say about the coefficient? Yes?
A naught prime should be equal to 0,
Yes?
and an prime is equal to an lambda n.
Yes.
Bn prime is bn lambda.
Can you sign back the paper, please? So this guy has to be 0 because here you don't have it. This guy is equal to lambda n an. This guy is equal to lambda n bn. Right? So you have a 0, prime is 0, an prime is lambda n an, bn prime is lambda n bn. Right? Alright, so I explain again. So I take the derivative in time of u, I get this series. I take the derivative in second in x of u, I get this series, but the second derivative can be replaced by lambda n cosinus. Now I identify the coefficient and I found that a 0 prime has to be 0. This coefficient has to be this coefficient. So an prime has to be lambda n an. And this coefficient has to be equal to this coefficient. So bn prime is lambda n bn. Right? Right. So on Thursday we have the midterm.